Okay, is everybody in? Ceremony is about to begin. Okay, so fast forward to 2002. Okay, so we're talking about a model for replacement still. Households or individuals' replacements of their cars. They're not just making binary choices. When you choose to replace your car, you think about, okay, what's the next car that I want? Should be a Volvo, or should be like a Mercedes or Kia. And if you choose a Volvo, it's going to be a brand new one, or it's going to be 2 years old or 3 years old. And what are you going to do about your old car? That's what this paper is about. This is going to be equilibrium because the prices at the secondary market, they have to kind of equate supply and demand. Okay? So not everybody is demanding 2-year-old Volvos, and nobody want to sell their 1-year-old Volvo that age. So we're going to try. We're going to have an extra loop that try to find the equilibrium prices at the secondary market. And so that's why we call it the doubly nested fixed point algorithm, because it's a fixed point algorithm to try to find that fixed point there. Okay, this is joint work with Fedor and Ken Gillingham, Yale, and Anders Munch, Copenhagen, and John. So that's, yeah, the paper is out there, and it's also in the box. Okay, so let's talk about Denmark. We're going to use Danish data. So the question is, how much is a Volvo in Denmark? This is the Volvo XC90. It's a little bit older picture, okay? But at the time, it's supposed to be new. It got the whole 9 yards, leathers, massage seats, and everything. So it's kind of a high-end SUV. I guess Americans would say this is a small car, but so it's $200,000 in Denmark, and so it's pretty expensive. The price in America is, at the time, $62,000. So that's because we are taxing cars heavily in Denmark. We have we used to have 180% registration tax. And then on top of that, you also paid 25% value added tax. So you pay taxes and taxes. And literally this like triples the price of that. Okay, and here this is just another car. It's a Toyota Avensis. Here you got Denmark, and sorry for not having Switzerland here. You're not in the EU, so you're not in the table. 180% value added tax before the, and then plus the value added tax. Registration tax 180%. Okay, now this is the price before tax, actually. So this is what we're working on now, trying to understand why the prices before tax is so cheap, right? Then we need to have like a competition in the primary market and how the firms are setting those prices. That's a dynamic game with this model embedded inside. We're not quite there yet, but that's what. Okay, so for now, we're just going to take those prices as exogenous. Okay, a little bit about Denmark. So the annual revenue of taxes is something in the order of 30 to 50 billion Danish kroner. Divide by 7.5, you get it in euros. So this is like 2 to 3% of GDP, 4 to 7% of annual tax revenue. So this is a lot of money. Okay, I mean the tax revenue is already high, so not that I'm complaining. I love taxes. We live on the Danish welfare tax, but we're just trying to say if you're moving around taxes here, you better be right? We're moving out. There's some room for lots of redistribution between people. So most of that tax originates from the ownership and registration taxes on new cars, and then fuel taxes. That's not so high because otherwise everybody's going to drive to Germany to fuel their car. But I guess the policy question here is, what are the effects of switching those car registration taxes from purchase to usage? Also, because, you know, if you think about what is it, you want to achieve the reductions in CO2, and you only think about CO2 emissions as those being, you know, emitted from Denmark. We're not producing cars. Then how do you reduce that? Well, that's if people they are using less gas, because cars are produced in Germany. Anyway, so we want to build a model that can answer this question. So here it is. Okay, so here's the model. We attempted to call it circular steroids. Okay, so there's going to be consumers, unit mass, infinitely lived, so like Aristocrat, infinite horizon. There are going to be different types of consumers, rich and poor, people with more, longer or shorter commutes. And they make ownership decisions whether to keep their current car, whether to trade it for another one, then whether to purchase it, that's just get rid of your car, sell it at the secondary market or scrap it, and then not get a new one. And then if you have a car and you have to move on, get a new car, no car, then you have to think about what to do with the old car. So that's like an endogenous scrap it decision, or a sell decision. In that case, you supply it to the secondary market, which kind of make prices increase in those cars. Cars are indexed by J. Okay, so there's different types of cars and different ages of cars. So now you can choose combinations of ages and types of cars. So think about cars J being big, small, green, brown, or different brands. This is constant for the car type. And then the age is changing, right? It's getting older every year. There could be forced scrappage, so we allow for stochastic accident, or you can scrap because you just think that you're not going to get enough money for it at the secondary market. And then we're going to add some consumer heterogeneity into all these choices, some idiosyncratic shocks through all these discrete choices. And we're going to assume that ID extreme value or generalized extreme value, so you get like a nested logit instead of or a logit model. And that gives us all what we just talked about, non-degenerate choice probabilities that are differentiable and smooth, and also existence of equilibrium in this case. Okay.
We got just clarification. Yeah. So age is the only thing that characterizes the car. Plus type. There's not like different drivers, different heating problems, right?
No, everything that characterizes the car that is not captured by those two variables is going to be ID extreme value. And in fact, later, since we want to have also choices of how much to drive those cars, we are kind of assuming that people making those choices, how much to drive the car, they're not thinking about the depreciation of the car. The only way a car is depreciating is through the age. If you want to have that, which can be done, well, then you need to have a state variable that captures, right? So how much is the mileage of the car? And then you have like an additional state variable. Yeah.
And the probability of accident depends on the car type and not on the consumer type?
No, it doesn't depend on the consumer type yet, but I know what you mean. I have a 21-year-old son. He's driving very carefully, but yeah, I see what you mean. Of course, models are approximations of reality, okay? And this is one of them. Okay, so here is how you do it in the aggregate picture, okay? So it's called the doubliness to fixed point algorithm. Like before, we're searching over the parameter space to maximize likelihood. And then there's an inner equilibrium solver that for each vector of prices, you can calculate the excess demand for each of the goods in the market, okay? Then you vary around those prices to get that excess demand. How on earth you get excess demand? Well, that's written down here. So for every trial parameter, you need to solve the single agent fixed point problem given that array of prices. Okay, so we solve the Bellman equation for all these different types of consumers. And that gives us all the choice probabilities of choosing all these different car trading and holding options. Okay, from that, you can compute the state transition. What I really glanced a little bit over at the end, but Theo's going to explain that in detail. That depends on the prices, right? Because it depends on choice problems that in turn depends on the prices. Okay, so it's going to be something called this trade transition matrix, and then there's the aging matrix. Together, that gives you the state transition matrix. So given that state transition, well, then you can calculate the stationary holdings distribution. That is how many people have cars that are age 1, 2, 3, 4, 5 of different ages. Okay, and you can also do that for the different types of consumers. Given that, you can aggregate up and calculate the excess demand. Now, excess demand should not be 0, right? It should be 0. But it's not necessarily 0 when you start with P. That's just an arbitrary vector. Then that's what you do in this inner equilibrium solver. You search for those prices that put supply equal to demand, given the demand and supply dictated or by the single agent and programming model. Yes.
Where is the supply coming from?
Supply. I'll say intuitive. Fedo's going to talk about it, but supply. If I have a car that's 5 years old and I buy a 2-year-old car, then I have to sell it, and that's the supply of used cars. Then, of course, the supply of new cars, and we just take that exogenous. Okay, that's infinitely inelastic supply of new cars. And you can always scrap them at the given scrap prices. New car prices are given, scrap prices are given, but the used car prices are going to be endogenous. Okay? They determine the equilibrium.
Are people allowed to sell their car and not buy a new one?
Yes. Yes. In fact, I'm going to go through all the choices now. Okay, so in a little bit. So just a little bit about the utility. So Feo's going to put functional form on. Basically, people get utility of the car. Okay, that depends on the type of the car, the age of the car, and then they have to pay some operating cost, and there's some trade and transaction cost involved. If you buy a new car, well, you have to pay the price of that car. If you buy a used car, you have to pay the price of the used car. If you sell one, well, you get some money back and so on. I'm going to provide the details of that. And then there's going to be these discrete choice epsilon, just discrete choice specific epsilons. Okay, we like to think that the utility is decreasing in the age of the car, but that's an empirical question. So we're going to estimate the parameters of those utility functions. But we expect it to be decreasing because people get declining utility of car services and increasing maintenance costs and so on as cars are aging. And then we're going to estimate marginal utility of money and allow that to be heterogeneous across different types of consumers, different incomes. And then there's the epsilon shocks, which is going to take the role of these chase shifters. I'm going to assume here for the presentation the ID extreme value, but in the model we have a generalized extreme value and a nested logis structure. Okay, so here's the choice tree. So before there was only 2 ways, replace or not replace. Today you wake up in the morning with a car, you can decide to purge it, okay, get rid of it, in which case you have to think about what to do with the old car, right? Scrap or sell. You can keep it, and then there's no scrapping or selling choice. You just have the same car, and the next period is just a year old. Okay. Or you can replace it. You can choose to buy among different types of cars here indexed by J, and it could be a new one, it could be a used one, all the way up to the oldest car -1. We call A bar the plunger. You can't buy the plunger. That's just not traded. But in any case where you replace your car, you have to think about what to do with O1, and that's reflected by these decisions. Okay, so here's the trading problem for a car owner. This is also a simpler one for people who don't have cars. They are not thinking about how to sell the car they don't have, right? So here's the choice-specific values. So if you are keeping the car, well, you get the value of keeping. The purple here is choice, and the states are in green. Okay, so this is like you wake up in the morning with a car of type A and HA, and then you trade in for a car in purple. Here it's just kappa that indexes keep, so that makes your car in the next period the same type but just 1 year older. And this is the one that we have here, right? So you get the current utility of whatever car you have today, and then here you got the discount factor and the expected future value of the keep choice. What does that give you? Well, if there's no accident, this is the accident probability, it's just going to age 1 year. If there is an accident, well, it goes directly into the clunger state and it has to go in the scrapyard. Okay. Now, there's other choices. Here's the essentially the choice of just the purchase choice and having choosing no car, kind of corresponding to this here. There, you need to make those sell scrap decisions, which is just a binary choice. This is actually all static. So known this. I mean, once you know the value functions, but you don't. That's. And then there is the trading choice here that corresponds to these different choices here. So let's go through them slowly. Now, if you are getting rid of the car that you have and you put it on the scrapyard, this is the scrap indicator. Well, you get the trading cost is going to be, you get the scrap price. Okay, you still get utility of having no car because you have no car to drive, you just get rid of it. Okay, then there is if you choose to not to scrap it but sell it, well, then you get the market price P. Those are the prices that we are trying to solve. So now you see here how the prices they affect the utilities. So you need to know what the prices are in order to be able to solve the consumer problem. And then there could be like sales transactions cost that potentially could depend on the whole array of prices and the type of each of the car. It could be multiplicative or additive. Yeah. And then if you choose to get rid of your car, well, you end up without any car tomorrow. So that's what we signify by this empty set. Then let's look at this last guy here. That's a value of trading for a car of type JD. Okay, so it could be different from the car that you have. It could be the same type of car. You just trade for 5-year-old Volvos all the time. But it does involve a transaction, unlike keeping if you're buying the same car, right? So you have to pay pay buyer's transaction cost because you're buying a car. Here is a person that scraps his whole car, so he gets a scrap value. But if he were sell the car because he's not scrapping, well, you would get the market price for the car that he's putting on the market. Okay, and here is what you pay for the car. That's the market price of whatever car that you've chosen. Yes.
So what's the P in the transaction cost?
That's to allow, for example, it could be that suppose there's really high transaction costs on Lamborghinis. Okay, then it may be that those transaction costs are, for example, proportional to the price or some function of the price. So it's just to allow for that.
So is the P like some kind of average price of that type of?
Or it could just be the price for the car that you're trying to sell. It's just, we could potentially allow it to depend on the whole vector. So we're just putting that in.
So it could be PGIA or PGD or?
Yeah, it could be both. or it could be like the price difference between what you come with, and if you trade in a Porsche for a Ferrari, then maybe it's different than if you come with some other car, or if it's on the same brand. You could allow that, but we're not doing that. We're just taking a proportion.
What is T and what is alpha?
T, alpha is the accident probability.
All right.
Okay, in fact, those accident probabilities, you could also let those be dependent on the type of the car. I haven't thought about how to do it with depending on the type of consumer. We could do that. Right?
What is a T, capital T?
Capital T, that's the transactions cost function. Okay, so it's a function here of whatever you are trying to sell here. So this is the sales transactions cost. This is the buyer's transaction cost. It's function potentially of the prices and whatever you're trying to sell about. Any more questions about the model? Yeah.
I'm not noticing consumer heterogeneity here. Is it just a preference?
It's just because it's not there yet.
Okay.
It's gonna where the consumer heterogeneity is come into some of the parameters, like for example, the marginal utility of money and people's preferences for cars and so forth. Yeah, he'll get back to that. I'm not doing that. Okay, I just want to try to give you in the light of Hirosaka, the structure of the model here. Okay, so now we got all the choice probabilities, right? But it do depend on the expected value functions and the prices, and these expected value functions are also, implicit functions of the price. So we have something like this. Because we have the epsilon shocks, we're going to have expected values being the log sum of all those choice specific values. In here, well, we just saw EV was in all the right-hand side variables here. So this is like a function of the expected values, right? So you've got a mapping from expected values to expected values given a price vector. So this is what we're just trying to express here, right? So the expected value function is the fixed point on this Bellman operator. But since the Bellman operator is indexed by those prices, the fixed point is also going to be an implicit function of those prices, just like parameters affected the Bellman operator and the fixed point before. Okay. So once you got that fixed point, well, then you can calculate all those expected value functions, put them into the choice specific value functions, and then you got your choice probabilities that are mostly logistic because of those ID stream value. Okay. Of course, here they also implicitly depends on the prices. And I think this is where Fedor comes in. Yeah, but before you get to speak, I like to do a little thing. I want to say in the repository, there's a link to this code, okay, and you can run it. Sorry, it's in MATLAB, okay, but and if you do that, there's, I think the two entry points is there's one file that's called run illustration that's just replicating some of the oh, not that one. Run illustrations. That's just replicating some of the figures you will see Fedor showing. And then this, so it solves the model. Okay, that's the entry point if you want to learn about that code and how to do it. Then you try to solve the model before you estimate it. And then there's something called run estimation. Okay, and it is going to take like 15 minutes to estimate this model because there's I collect them and all sorts of stuff. And you see, it's kind of getting started now. And I think maybe if you make the rest of the talk, it's probably going to be done before or interrupt you.
So I have to start with a 20 past.
Well, it's already done the first iteration, right? So you don't have much time.
All right, so thanks for
Oh, maybe you should just change
Oh,
it.
how do I get back?
Let's just go there.
So not only Bertel is preventing me from starting to talk, it's also setting up a time bomb to interrupt me later. But okay, so let me, is this working? So let me take it a step further. So what you've seen now is that we can model dynamic discrete choices of individual economic agents in applications to kind of simpler model by not just you know the two alternatives or many alternatives. And now we want to implement this you know triple nested loop. And Bertel has talked already about this, but let me just repeat. You know, the big picture is that the nested fixed point estimator was solving the dynamic problem, and then the solution of that problem was informing the likelihood function, right? Which John maximized over the set of parameters. Now we want to think about the equilibrium. So let me start talking about the equilibrium calculation and how that comes in. As was pointed out absolutely correctly, in this market, in the market of secondary cars, there is demand and supply, and both kind of comes from the same type of agents. People who want to sell their existing cars are supplying second-hand cars to the market. Some people want to buy second-hand market. We will also have the scrappage and the new cars coming in. And so I'm going to be talking about this intermediate level first. On this level, again, what is happening, we want to solve for the market clearance condition. And this is where the equilibrium object, this price, will be determined. And in order to do this, we are resolving many times the dynamic programming problem. So we are resolving the dynamic programming problem, the Karon-Zucker problem, you know, given a vector of prices. Okay, and therefore, you know, and this is done in order to clear the market, find the equilibrium prices, which correspond to the optimal dynamic behavior of all the people in the market, such that it clears. And that now produces the choice probabilities that we can actually take to the data in the likelihood function. And so now, right, there's an additional kind of loop where we're resolving the dynamic programming problem a lot of the time, a lot more number of times. And this is running right now on this laptop. Optimizing over 131 parameter using 39 million observations. Yeah, yes.
On one core.
So
Parallelize. On one core. So let me show you how it's going. All right, so let's start thinking about the equilibrium on the secondary market. We will, you know, make strong assumptions. There's no way around that in this particular model, especially if we want to, you know, to make it feasible with the estimation. So the new cars, we just basically assume away. The new cars will be supplied to the market at the fixed price. Okay, one other kind of note I should say is that this paper was written as part of a bigger project, and this paper is a computational framework, really. So if you have, you know, a situation where durable goods are traded, and you need to include into your policy analysis the fact that there's a secondary market for any sorts of durables, this is the computational framework to do it. Okay, and so within this computational framework, we're fixing the supply of the price of the new car, and yet it's completely possible to embed this into some sort of competition model between the car producers, right? Under the assumption that this competition would take into account the effects of the secondary market. I'm spending too much time. Infinitely elastic demand for scrap cars. Remember, this J indexes the type of car, so all cars of the same type will be scrapped at the same price. And so what we're left with is this capital J of A bar minus 1 endogenously determined used car prices. This is the equilibrium object. So we have capital J of types of cars. Each car starts as new, the new price is fixed, ends as a scrapped car, or a scrap, the terminal age of the car A bar, which is here. Did you mention this terminal age? It's like in a life cycle model, right? Think of this being 110 years where people primarily are all dead, right? So this is not something that puts a lot of restrictions on the model. It's just a bound on the age of the car. But what we're saying that if you get into this
accident, then the car transfers to this terminal H immediately. And then what's important about it, what's special about this terminal H car, it cannot be sold on the market. It just has to be scrapped in the beginning of that next time period. All right, so we have this number, the J capital A bar minus 1 products on the market and so many prices that we need to calculate. All right, so how do we do that? Well, we assume that there is a continuum of consumers, okay, on this market. And let's start with the assumption that they are all homogeneous. They're all the same, except every consumer on this market gets their own realizations of the extreme value shocks. Okay? And so they're not really homogeneous consumers, they're idiosyncratically heterogeneous consumers, right? They're different by something that we don't observe. And this shocks change every time period. They're serially uncorrelated. All right, so we start with this framework and then enrich it with consumer heterogeneity. We will worry about this distribution of consumers across cars. These are like market shares. This long vector of the dimension J capital times the terminal A plus 1, right? That tells us what's the fraction of consumers who own a particular type of car of a particular age, and the plus 1 comes from the people who don't have any car. Okay, is that clear? This is going to be part of the description of the equilibrium. Now, let me come back to the timing assumption. This is also kind of purely technical. It could be done in a different way, but we assume that people start the period with the car they own, and then immediately at the beginning of the period, there's this trading phase, which takes no time. Cars change hands, on the secondary market, and then whatever car is left after the trading stage, that car is being used during the period, might get into the accident, and then the next period, people start either with their 1 year older car, or if they had an accident with this terminal age car, which then in the trading phase in the beginning of the next period has to be scrapped. That's the timing assumption. And so that makes it impossible, it says here, right? The cars purchased in any time period as new are accounted as 1-year-old cars. In the state space, you cannot have new cars because in the state space, which measures the car ownership at the beginning of the time period, the newest car is going to be already 1-year-old. This is, again, just to understand what's happening here. So what's the equilibrium? We're thinking about the stationary equilibrium, okay? And this is the pair of this distribution of ownership, the ownership distribution vector, which I just defined, and the prices, the vector of prices, which prescribe a price to each type and each age of the car, such that consumers maximize their expected discounted utility, secondary market clears, and the ownership distribution is time invariant. Okay, so that's quite a natural way to define the equilibrium. Let me say that, okay, consumers maximize their expected discounted utility. That's kind of already done, right? We are solving the dynamic problem, which results in the choice probabilities, conditional choice probabilities for all different choices that Bertel has described so well, which all depends on prices. And then let me start talking about these other 2 conditions, and I will start from the ownership distribution. So what's the dynamics of this ownership distribution? How does it change? It can change for 2 reasons, right? There can be trade, and cars change hands, and that brings change into the ownership distribution, or time passes and cars age, and then that can also has to be accounted in the ownership distribution in this vector of market shares. Yeah, let me come back to this. So let's first look at the transition probability for the ownership distribution resulting from the trade, okay? How does trade happen? Well, how do cars change hands in this trading phase? That's all governed by the choice probabilities. The choice probabilities which come out of the solution of the dynamic programming problem. And so by combining all the many choice probabilities into kind of a specially designed transition probability matrix, we can say that if you had an ownership distribution in the beginning of the period Q, then we want this matrix to be such that Q times this omega of P is the distribution of cars owned by people or right after the trading phase. Okay, that's the idea under this matrix. And you would agree that this is nicely block structured, and you can see that, you know, on the diagonal there's this a sum of two blocks. These different matrices take into account the fact that some cars are not traded; they're being kept. This is the capital lambda blocks. And then this delta ij's, these are the blocks describing the choice probabilities, or composed of the choice probabilities describing the trade of cars of type I to type J of different ages. Okay? And then you have this additional row and column in this transition probability matrix, which describes the changes of the people who didn't own the car, who don't own the car in this in the beginning of the period, and those who transition to not having a car. All right? Yes.
Which say axis of the matrix, or which one is the before trading? Which one?
So
is after trading?
this let me think. So this needs to work. So yeah, this is standard transition probability, right? This describes from which cars that you had to, you know, this sums up to one along the rows.
So which the rows sum to one?
The rows sum to one. This is your future car in the row, and you know, this way it's the existing car, this is your next period, or after trade phase car. Oh, did I switch to the new slide now? Okay, now once that's happened, we want to take into account the aging of cars. And now you will see that this matrix that describes the transitions due to aging, it's actually block diagonal, because cars, when they age, never change their type. So all the aging happens within the type of a car. And what is this aging? Well, it's stochastic in the sense that, you know, with 1 minus alpha, the car will be 1 year older, but with probability alpha, it jumps to the terminal age when it has to be scrapped. That describes that's how we model the accidents. And you may have a question of what's this last row and why it's the, you know, what's this first element? Why is the last year age car with some probability becomes 1 year old car? Well, that's because on the previous stage over here, we put the choice probabilities of buying new cars in place of those oldest cars, so the last row in this trading matrix. And we can do that because the terminal age cars cannot be bought, right? Can be demanded. And this kind of undoes that little trick to keep the matrices of the right size. And so the big idea here is this: you start the period with the ownership distribution Q. After the trading phase, you get this Q times omega of P. And then when you take this vector and multiply with Q matrix, you have the ownership distribution in the beginning of the next period. All right? And so that means that the stationarity condition essentially just implies that we need the invariant distribution of the implied Markov chain. That's how the stationarity of the equilibrium manifests itself in the setting, and we immediately have uniqueness if the sigma, the weight of the extreme value distributed component in the preferences is positive, then we have full support in this omega of P, and we immediately have irreducibility and aperiodicity of this Markov chain. And John is nodding, this is very good, which is essentially gives you uniqueness immediately by the fundamental theory of Markov chains. Okay, this is uniqueness of the ownership distribution in this equilibrium, but that's not all. What else do we need? We need to find the prices that clear the markets. All right, how do we construct? One thing I have to also say here, it's not only that it's unique, it's also shown in the paper, in the theorem in the paper, that this implied equilibrium ownership distribution is a smooth function or a continuously differentiable function of prices. And that follows essentially from the same ideas that Bertel talked about, you know, with the extreme value shocks, you smooth out everything in the problem. So the fixed point in the dynamic problem is a smooth function or is continuously differentiable function of the structural parameters, and prices kind of play the same role in there. So we get this Q of P implied by this condition, which is a nice function to work with as we move on. All right, so what's demand? This is the demand for cars of type J of HD at a particular price given the ownership distribution. This is calculated by essentially just mechanically combining demand for this particular car JD from people who own the cars IA, right, type IHA, corresponding fraction of the population. We basically multiply the components of this ownership distribution vector with the corresponding choice probabilities. And this first term here takes care of those people who don't have a car, but want to buy a car JD. All right. Same thing with supply, a little bit more tricky. Supply comes from people who do not want to keep, and this pi kappa is the probability of keeping a particular car JD. But they also don't want to scrap it. This pi 1 sub s, this is probability of scrapping a car JD. Okay, and then we have to calculate the demand from all those who actually own car JD. Right? Excess demand is obvious from this. We just put together all of this individual demands for different types of cars, and we end up with J times terminal H minus 1 equations. That's the number of products which are traded in the secondary market, for which we can write the supply and demand. And remember, that's the number of prices that we have. That's the number of elements in the price vector that we need to compute in order to clear the markets. So exactly identified system, non-linear, unfortunately, but these are the conditions that define the equilibrium that we are modeling in this paper, stationary equilibrium. This is essentially just the condition that you saw, plus the solution to the non-linear system of equations which clear the market. And we show the existence in the paper very carefully. Yeah.
But the uniqueness of Q is conditional on P, but the P you don't have to do.
Exactly, that's exactly right. So conditional on P, Q is unique, but we don't have uniqueness of P. So this is only existence. So like half of our equilibrium is unique, but the other half we haven't proven yet. So.
But we haven't seen.
But yes, the disclaimer applies. We've never seen a multiplicity of equilibria in all our numerical exploration of this model.
An alternative version is we haven't looked carefully enough.
Exactly. So this is cheap talk for you. But now what's interesting is that, let me go back to this note over here. It turns out that you may still have the question kind of floating in your head. What happens with this scrappage in new cars? We are not fixing the market at either ends, and so how does it function? Well, it turns out that we can prove that there's this flow property in the stationary equilibrium. It is guaranteed that the fraction of cars which are scrapped, and this is scrappage which is endogenous, right? People choose to scrap the car rather than sell it on the market. That endogenous fraction is exactly equal to the fraction of new cars of the same type which are bought in that period. So you have this, stationarity across time as the ownership distribution doesn't change, and you have this constant flow of new cars and scrapped cars in each time period in this market. And in that sense, that's a little bit artificial, but it's a nice construct. What's the time? All right. So now, how do you compute this? And here, the answer is, how do you compute it quickly? The answer is very, very simple and kind of standard gradient-based method and derivatives. In our case, these are analytical derivatives. And moreover, with this triple structure kind of reflecting the nested fixed point structure, and Bertel had talked last hour about how you can reuse derivatives on the inner circle to construct derivative on the outer circle. We're doing this here all the time, right? So we are reusing the derivatives calculated for the Newton step in the dynamic programming problem in order to calculate the derivatives of the excess demand function, and those then come into the derivatives of the likelihood function. And then we're using BHHH on the outside to approximate the Hessian. Okay, that's one thing. That's backwards propagation I've learned recently. We're reusing derivatives and using chain rule all the time, but in this kind of, a different sense. All right. The second very important actually element in making sure that this works fast is very good starting values. Newton in general is not globally convergent, and therefore you want to start really close to the solution to make it very fast. It turns out that in our setting, if we kill all of the transaction costs in the problem has a very simple solution. It's basically a linear system of equations. And without transaction costs, we can very quickly get a starting value for all our Newtons, which is sufficiently close. And that's, I think, is second really necessary component to make sure that your gradient-based method works really well. And for economic problems, this is a lot of the times possible to do. You just simplify your economic model somehow so that it can be easily solved, and maybe that provides really good starting values. So that's kind of the general principle. Okay. So now let's talk about persistent consumer heterogeneity. And we extend the model to allow for several types of this persistent consumer heterogeneity. It can be time invariant, it can be time variant, and it can be a combination of the two. So here we're thinking about observed heterogeneity, and you can have different levels of education or income. Income can change. This is infinite horizon model, right? So every time you're thinking about something that changed, then we will kind of translate that into the ergodic distribution of the corresponding Markov chain. Yeah.
Small question regarding the uniqueness of the equilibrium. Shouldn't it also depend on the starting values and maybe on the variety of the transaction costs, and so that you can search for the multiple equilibria varying those things?
Right. So very good question. Look, we have to distinguish between the theoretical setup, having multiple equilibria, and what you do with computation. And now the theoretical multiplicity can also be a function of all the things that you've mentioned, in particular the values of the parameters. So it could be that at the true parameters where the data was generated, there could be multiplicity. Or maybe there can be multiplicity at some other values of the parameters, and where the data was generated, it's unique. But even that theoretically possible multiplicity can spoil and make the computational method really struggle.
Mm-hmm.
And then, yes, because we don't have proof for uniqueness, then what you usually do in that case, you start your solver in different points and compare whether it converges to the same point, the same solution, things like that, right? And that's where we say that we haven't seen evidence of multiple equilibria in this problem. All right, so going back to this consumer heterogeneity. So we can allow for all of this. We repeat the theory, the existing theorems. The computation algorithm is modified, but it's linear in the number of consumer types. And what actually happens is that now you have to ensure that each subvector in the ownership distribution, which corresponds to a particular type of consumer, is time invariant. Okay, and that gives you, multiple invariance conditions for the ownership distribution. Well, thankfully, these are pretty easy to calculate, actually. And this has to hold for every tau, where tau indexes either the time invariant consumer types or the consumer types in the ergodic distribution if they're time variant or combined. But then the main thing is that we clear the market as one. Right? These F's here, the F tau, these are the fractions of consumers of different types. And so we want to make sure that the excess demand is equal to 0 across all of the consumers. That allows consumers of different types to trade between each other, right? That's what it allows to happen. And then you are seeing things like sorting consumers into particular types and ages of the car. And which hold new cars, new better cars, and poor can use the older cars. You have gains from trade, right? This is the kind of the main thing that you want to be able to address with this model. Okay, so here's an example of gains from trade. Bertel was visiting John in Georgetown a few years ago, and they had this wonderful exchange of an old Volvo for a price of $1, something like that. And John got himself a new Volvo.
I have a very poor FICO score, so I couldn't get like the Mercedes that I wanted, so I had to go in the secondary market and then see how happy these guys are.
Yeah, both of them. See,
Both
you
of
know,
them get.
Gains from trade works for all the parties. But here's a little simulation. In here, we have two types of consumers. They differ in their marginal utility of money. And the market with just one car of different ages. You can see the ages go all the way to 25 years. With the normal transaction costs, you see that already here that we see the rich guys are kind of sorted into the new cars. This is the stationary distribution of ownership in this market. And the poorer guys, they sort into the older cars, and there are more poor people who don't own the car in this last column here. But as you increase transaction costs, the effects of that change in the policy is going to be heterogeneous across the consumer types. You know, the poorer people are pushed out of the market first, a lot quicker, and a lot more of them end up not having a car if you increase transaction costs for whatever reason and kind of suppress the market. Okay.
But it also reduces the number of rich people buying new cars, right? Because they are depending on selling them to the, you know, that poor economist on the right.
Yeah, that's right. So you're talking about this increasing as well?
Yeah.
Yeah. Well, these are implied equilibrium prices, which are, by the way, not restricted by anything, you know, beyond what we've described. And it's kind of nice that you get this downward sloping demands and no negative prices anywhere. And you can see that the price falls really pretty far down and then stays flat in all of these calculations. And that's kind of determines the actual age of the fleet. Even though so what I want to say is that a lot of the cars are scrapped around here. So in some sense, this model allows for endogenous scrappage, and it allows for simulating the policies which may affect, you know, the average age of the fleet of the cars, you know, cash flow clunkers and programs like that. So if you want people to, you know, scrap cars faster or hold them for longer, this framework is actually very good. It can take care of that, of those effects. All right, so if there are no questions for that, I'll go to the estimator next. And so we're now talking about the outer loop. And we didn't change much on the outer loop. We've calculated the dynamic programming fixed point many times in order to clear the market. And once that happened, we can calculate the choice probabilities corresponding to the equilibrium. And these choice probabilities can be essentially just plugged into the likelihood function. And the likelihood function is formed in principle in the same way as in the Harold-Zarker problem. One twist that we introduced here, and you know, talking about how many again? 31 million? A lot of millions of observations of registered data in Denmark. And in Denmark, we essentially observe the population of cars for 14 years, and including all of the transactions and people who own those cars. Now, this would take a lot of time to calculate likelihood with that much data. But because we assume that our heterogeneity is observed, and we can also prescribe types to cars which are observed. Now, we really only care about this number of transitions from a particular state in the data to a different state conditional on the consumer type. And this huge, massive data set can be represented by this count of transitions, which makes it also very easy to work with. Question?
Yes, sorry, I have a data question. So, since you observe ownership each year, is stationarity also a feature?
That's a wonderful question. So I've mentioned that this is a part of a bigger project. The bigger project is non-stationary equilibrium, because data does display non-stationarity. You would imagine that in good times, more new cars are bought compared to the bad times. That's exactly right. What else should I say? We're still working on that, and we're hoping to maybe apply machine learning techniques and deep neural nets to help solve that problem, which happens to be and appears to be a lot more complicated. Yeah.
What exactly is NX? Is this just the status of your
This
J,
X.
of your car types and the age of the car you own, like the type and age of the car you own, or?
That's
is there
right,
other
that's
stuff
right,
that
yeah,
you're-
yeah, that's the X. And that has to be paired with your observed consumer characteristics, which are in town.
Okay. And
So-
how,
so this is-
what is the data that's in?
Yeah, let me get there.
Oh, you're-
It's gonna be, in the application, it will be specified,
So, but X is a dimension JA plus one, or JA ceiling plus one.
that's right. And then the likelihood of our data, if we have data expressed in this count, is just essentially the sum over all of this transitions, you know, where you take the log of the choice probability corresponding to that transition. A weighted sum, should I say, okay? What else do I have to say about maximum likelihood? B triple H. We have all the analytical first derivatives, and so B triple H is a very natural choice to approximate H. Yeah.
Can I ask, given the size of the problem of the pop-ups, that the CCP estimate would be the first starting point? The reason why you
Why are we not using the CCP estimator?
Many empty cells and zeros and stuff.
In this n, so many of these n's are zeros. We have many small cells. And in this project and another project, we have a feeling that a lot of interesting stuff actually happens in the transitions which are not numerous. Right, and if you do a usual frequency estimator for the CCP, you lose precision exactly in those parts of the data which inform a lot of the parameters of this model.
Another thing is we don't have the used car prices. We only have the new car prices and the scrap prices. And so how do you put those prices into the CCP estimate?
All the choice probabilities are dependent on prices, and we don't observe them.
But you have a nesting structure,
Yeah, so we would have to solve
Yeah.
part of it, yeah. Okay, so in the remaining 15 minutes, let me go very quickly through the Danish application. We're modeling the secondary car market in Denmark. I've already said something about the data, but here's the motivation. This is part of the IROOT reform in Denmark. Is it being completed right now? It's a long project. This is Intelligent Road Use Charge. That's what IROOT stands for. And the idea is that, you already know that the new cars are taxed in Denmark very, very heavily. Well, maybe those taxes can be lowered, and instead something else like usage taxes could be increased in order to shift the ownership and the usage patterns for these Danish drivers in some socially beneficial way. So, for example, you can fight congestion by these tax changes. So, what we are interested in, we're interested in the equilibrium dynamics of car ownership and type choice. We want to understand the new car sales, the fleet age. Oh, another thing is you can imagine that the age of the fleet in Denmark is pretty high, right? With very high taxes on the entrance into the cars into the country. And with the recent developments in the technology, you probably want more new cars to be driving on the streets of Copenhagen. And so that's another idea and goal with the change. So what we do in this application, we estimate the model using Danish register data, and then we run counterfactual simulations, as we usually do in structural econometrics, right? We cut the registration taxes by half in that case, and we increase the fuel taxes and see what implications that has for the ownership patterns and for driving of cars in Denmark. The question.
Briefly about the context, what about these taxes for the used cars? Is it just the same by purchase price or
You don't pay tax.
I'm so glad I have.
For the used cars. I mean, I could just sell a car. Maybe there's a little transactions cost involved of changing plates and stuff. But the 180%, no, that's just inherent in the used car prices. So because prices are high, new cars, you're gonna see high used car prices as well. But it's not like you have to go to the tax office and do a part of it. It's just no transactions.
So essentially, no taxes on the used cars. all the taxes.
Prices will be high anyway, trust me.
You expect like a lot of used cars being imported into Denmark?
Well, then you have.
On the import, there is a tax. And then you don't see any used cars imported because it doesn't make sense, right? It's rather, it's economically better to import a new. Okay, I'll have to really rush through this, but the main points are that we, given the computational framework that we've described, and you've noticed the functional forms were all left unspecified for the utility, for the transaction costs. There's a lot of flexibility in this computational framework, but in the application, we have to specify a particular utility function. And we have this utility of car, which depends on age. And we want to talk about driving. So we want to put driving into the utility function, into the preferences. And we use the quadratic utility of driving, depending on the x, which is the amount of driving, and the car characteristics. Now, the fact that within the computational framework, all the dynamics go through the age of the car is a big simplification, as already have been pointed out. But given that simplification, we can completely separate the driving choice from the transactions, from the choice of changing and trading the cars. Right? So it's as if the optimal driving can be calculated conditional on the car that you have and other things like cost of driving or efficiency of the car, fuel efficiency of the car. And this choice can be treated completely static under the assumption that people don't take into account how their cars depreciate as they drive. More, beyond how it depreciates because the car ages. Okay, so that allows us to essentially write down the flux for the driving and have an equation, a linear equation of the amount of driving which we observe as a function of the car age and the fuel price. This is fuel price, yeah. And then we thought of this approach to estimation of this problem. We can estimate this driving equation separately using data on driving, and there's going to be a lot of heterogeneity introduced into the parameters. And then in the same time, we can rewrite the indirect utility function as just a function of age and age squared of the car and estimate the choice model, the dynamic choice model, kind of freely with just these parameters U0, U1, and U2. And then once these two estimation exercises are done, then it's possible, it turns out, to recover all of the structural parameters and preferences from these two sets of estimates. And so this is the same as saying that, the model on the trading does not place any restrictions on the optimal choice of driving. And therefore, we are able to run the simulation part by part and then reconstruct the structural parameters of preferences from these two sets of estimates. So this is a kind of trick that is employed in this estimation exercise in this paper. But if that was not possible, right, then we would include the driving data into the estimation of the structural model, and that would complicate things a lot because we would not be able to write the likelihood function as a function of discount of these transitions. All right, I guess I'm not going to go through the specification, but in all details, but because framework allows for very free specification of various parts of preferences, we can include a lot of heterogeneity in here. We will focus on, let me just start, talk about here. We will have 8 types of consumers, and they are differentiated by the distance to work, by whether they're single or married, and their income. And this is a pretty simple, simplified exercise. It's not a full-blown. I mean, we could have done it to a much greater detail, but because it runs on the laptop, it should have finished.
Maybe it is finished.
Maybe
Try
it is
to go to
finished.
terminal.
Okay, let me come back to that. This in this paper, it's really an illustration, but which still, shows you the power of the approach and shows you some facts about Denmark, which are visible even at this level of aggregation. So before I go to policy simulations, I need to convince you that the model fits the data that we already have. That's a necessary step every time. And here's the model is estimated with maximum likelihood, but if we look at the predicted and actual market shares of different cars among different consumers, so these are the 4 types of cars, so I didn't say what they were. the cars are separated to heavy and light, and more and less fuel efficient, which we label brown and green. So this is light brown and light green, and heavy brown, heavy green. These are the 4 types of cars. Everything is aggregated to this 4 types, and there's a no car. And then on this plot, you see 8 dots of every color, 8 dots corresponding to 8 different observed types of consumers. And you can see everything lines up along the 45-degree line, indicating that the actual market shares kind of match, or predicted market shares match to the actual market shares. All right, these are the observed and estimated or predicted probability of purchase. As you would expect, new cars are bought a lot more often than the used cars, but we see a little bit of a shape here, a flat region. Well, maybe we're missing this little hump over here, but more or less flat up to about age of 15, and then it tapers off. And so the model is doing quite well on this aggregate prediction of probability of purchase. Now let's talk about the distribution. I don't know how much you can see of this graph, but this is the same kind of the ownership distribution plot that we saw in the example, except now we have 4 different types of cars and 8 different colors for different types of consumers. This is the data, and this is the model. Okay, and if I flick like this between the 2 slides, I hope you can see some correspondence of the colors. Or we can look also at normalized pictures like that. This is the data and this is the model. And we argue that the model has some bite on explaining the sorting of different consumers into the sectors of this secondary market of cars.
If you look at the lower bars there, the red, that's John, right? And the blue, that's Myrtle. John is always buying new cars, and then I tend to sort into the lower range. But you also see that in the data.
Light B and brown green, what are those things?
So these are a population of cars divided into 4 groups.
Are these actual colors of the cars?
No, they're heavy or light on both sides of the median, and they are fuel efficient or less efficient also on both sides of the median. So we take the population of cars and we chop it into by 2 dimensions into 4 groups. So yeah, this is quite crude, but we have not taken this framework all the way to to the frontier.
See, the problem is we wanted to give the data with the paper, and you just can't download the Statistics Denmark data. So we work with these 8 consumer types, but really the computer time is linear in the number of consumer types. So you want to have 100, and you have the data.
Yeah, you can parallelize that. At least part of that problem. Yeah, Bertel mentioned that we wanted to take the data out of the extremely very secure data zone of the Statistics Denmark, and we were successful because we aggregated the cars to this extent. And in fact, you do have in the repository all the data that is needed to estimate this model. Okay, let me finish. Just a note on the fact that you can see this, the calculated prices, which are implied, we don't observe them. And you can see there's little wiggles towards the end of life for the cars, and that was a little bit suspicious, but turns out that makes a lot of sense. It turns out that the cars have biennial inspections in Denmark, and it very much matters for the price of the used car, whether it just got an inspection or it needs an inspection next year. And therefore you see this wiggles of cycles of the length of 2. Okay, so just a few minutes on the counterfactual. The idea is that we can have the baseline, that's where the model is estimated, and imagine that this reform of changing taxes is done in the naive way. What's the naive way? We're changing taxes for the new cars, and we're changing fuel prices for all the cars, taxes on the fuel for all the cars. Well, we have to predict somehow how the prices of the used cars will change. And imagine that the policymaker says that, okay, let's just assume that the prices change proportionally, okay, and run a counterfactual simulation on that. This would correspond to what you can do with the model which does not have a secondary market and is not capable of predicting the changes on the secondary market. Okay, then we can calculate the realized equilibrium out of this policy change, and then construct the sophisticated policy which takes into account the reactions from the from the secondary market. And there's a big table of numbers, which is discussed in the paper really well. But let me just say that, you know, as you would expect, the naive policy doesn't, this is the naive policy tax revenue goal, but it goes a lot lower on the tax revenue in the realized naive policy change. And in fact, you have to reduce taxes, increase fuel taxes less than in the naive policy in order to hit the tax revenue targets. And so that made us think that Denmark is kind of over the hump of the Laffer curve in these taxes. Taxes are really high. And also we've calculated things like, externalities like CO2 emissions from the driving, predicted driving in different regimes, and started thinking that maybe we shouldn't aim the policy change at just the monetary goals, right? The budget neutrality of things like that, and look at some more broader implications of these changes, and started drawing pictures like this. This is the car tax, this is the registration tax, and the fuel tax. The red dot is the baseline. That's where we are now, and you can see that indeed, if you decrease the car tax or fuel tax, this plane increases. This is tax revenue. This is the indication that Denmark is indeed on the other side of the hump in the Laffer curve. But then you can make such plots for CO2 emissions, for example. What happens with the CO2 emissions when you change these taxes? This is all based on the counterfactual simulations of different equilibria. Or you can have a welfare measure, which is based on the estimates by the Danish Transportation Institute of congestion and other implications of driving. And you have this other surface, and then you can combine them all, and look at that. It turns out that if you change taxes within this green area, this green sleeve from the baseline, that's where you increase tax revenue, increase social welfare, and decrease CO2 emissions. So a structural model like that, estimated on real data, allows you to draw this policy maps, which sometimes reveal that there's a really nice direction in the change of taxes. And these other dots here, they would be the optimal policies according to different criteria. Okay, well, let me stop here and say that, going back, we've been talking about dynamic discrete choice, and a 30 years old paper, which is still cited pretty heavily, dealing with a simple choice of a particular guy. But this scales up to modeling processes still today, which are quite complicated and very useful. Hopefully we can be useful to as economists with the policy propositions of this kind of potential.